everybody, it's Mrs. Dunn again. I wanted to show you an example of a minimization problem. So we are going to solve the dual problem. So this is how we solve a minimization problem with problem constraints that are in the form greater than or equal to. So for example, what I want you to learn in this video is how to, first of all, form the dual problem, and second of all, interpret the solution of the dual problem. So let's look at an example. So here we have a minimization problem. So our objective function is c equals 16x1 plus 45x2. We're being asked to minimize this objective function subject to the following constraints. What I want to point out is you'll notice that what we're asked to do is to minimize the function, and the problem constraints are all in the greater than or equal to format. So what we do first is we create the coefficient matrix from this I system. So notice we have the coefficients of x1, x2, and our constants. x1, x2, and our constants. 2, 5, 50, 2, 5, 50. 1, 3, 27, 1, 3, 27. 16, 45, 1, 16, 45, and 1. So what we're now going to do is find the transpose of that coefficient matrix. Finding the transpose simply means swapping the rows and the columns. So if you remember from the previous screen, our matrix A was this matrix. We took this row 2, 5, 50, and it becomes the first column of our transpose matrix. So take a look at this. Each row became a column. Each row became a column. And this A transpose is the transpose of matrix A. From this transpose matrix, we are going to create a dual problem. We are going to create another linear programming problem. Notice instead of using the variables x1 and x2, we are using the variables y1 and y2. And we created this I system. So we've created the dual of the minimization problem. We are going to now maximize the objective function p equals 50y1 plus 27y2 subject to the following constraints, which are now less than or equal. Okay, so now we're solving a maximization problem. Now we're doing this the same way you did this in the last section where we were using the simplex method. So we're going to have to introduce slack variables. Now on the next screen, I have solved this entire problem. You learned this process in the previous video that I made for you. But what I want to talk about now is look at what I'm using for my slack variables. Remember, to start the maximization problem, we have to create an E system by introducing slack variables. Look at what we're using for those slack variables. We're using the variables x1 and x2. Okay, now when I show you how to interpret the final tableau, I think it'll make sense to you why we're using x1 and x2 as our slack variables. So this is just showing you the process. It's showing you, you guys remember how to find the first pivot, how to find the pivot column, and then the first pivot element, and then the second pivot column, pivot element, and finally we get this final tableau, which I've copied on the next page. So here's the final tableau. All right. This is the final tableau of a maximization problem. You know how to interpret this result. You learned in the previous section that the max is 420 when y1 equals 3 and y2 equals 10. Max 420. x1 and x2 are both 0 in this final tableau. Okay, now what's really cool is how we now, from this tableau, find the solution to the minimization problem. So the solution to the minimization problem can be found in that final row. The value, okay, so first of all, let me point out that the minimum of the minimization problem is 420. So the minimum is 420 when x1 equals 15 and x2 equals 4. It's kind of cool, right? So to summarize, we have the max is 420 when y1 is 3 and y2 is 10. But the minimum is 420 when x1 is 15 and x2 is 4. So an optimal solution to a minimization problem can always be obtained from the bottom row of the final simplex tableau for the dual problem. All right, good luck in this section. Great job.